Hey everyone, so welcome to my second lecture on the course Ordinary Differential Equations. So today we are going to see a method called as a variable separable method. So in the previous lecture, that means the first lecture, what did we saw was we had a differential equation and I gave you one function and I told you check whether the given function is a solution of the differential equation or not. And I also took two solved examples where we verified whether the given functions are solutions or not to the given differential equations. But then the question is how to find those solutions that we haven't talked about. So today we are going to see the first method which will help us to find the solution of the differential equation. So these are the two things that we are going to see today. So what is the objective? So at the end of this talk you should be able to find the solution of a first order linear differential equation. Not all differential equations. I will say some conditions. And we will also use GeoGebra to find the solutions and how to sketch the curves. So that's what the objective of today's talk is. So let's see what is the method. So the method is very simple. The name itself suggests. It says that so whenever you have a differential equation, obviously it will have independent variable and the dependent variable. So what you do is you try to separate the independent and the dependent variables. If you can separate the independent and dependent variables, then you simply integrate both sides. And if you can do the integration, you get the solution. So that's all. The method is very easy. So this is the first method we always try whenever we have a first order linear differential equation. Linear means degree 1. So whenever you see first order linear differential equation, your first thing is you try this method. If this doesn't work, in the next lecture I will come up with some more methods. See, let me tell you one point over here. Differential equations are not at all easy to solve. There is not one single method or one single algorithm to solve all the differential equations. No. There are plenty of methods. We see a differential equation, we choose a method and we solve the differential equation. Moreover, there are still plenty of differential equations whose solution we know it exists, but what is the actual solution we don't know. There exist such differential equation. Maybe in the due course I will tell you what are those differential equations. But then what do we do when we don't have the actual solution? We take the help of numerical methods, numerical analysis, and we also take help of direction fields. And using direction fields we approximate the solution. That's little bit on the higher side, but okay, let's keep that aside. Let's see the very first basic and the simple method, which is called as a variable separable method. So I gave you the idea. So let's see the example on this method. Okay, so if I take this first order linear differential equation, dy by dx plus 4y equals 1.4. This is first order as well as the linear differential equation. And as you can see, if I take 4y on the right hand side, then and if I divide this, so all the dependent variables and dy is on one side and dx is on another side. So if you see the second step, I could able to see the cursor over here. So I could separate the variables. Now the method says once you separate, you simply integrate both sides. So once I do integration, what is integration of this? It is ln of the denominator upon minus 4 is equal to x plus c1. If I take minus 4 on the left hand side, this is simple calculation which I expect you people to understand. If you don't, you can ask me in the comment section. And once I take, if I want to remove ln means log to the base e. What I will do, I will take exponentials on both sides. Why? Because log and exponentials are inverses of each other. So this is what I have. So I have y equals 1.4 minus c into e raised to minus 4x upon 4. So this is what the solution of this differential equation is. If you are not sure whether this is correct or not, whether your calculations are right or wrong, you differentiate this, you plug in over here, and if it satisfies this differential equation, then we say that that function is a solution of that differential equation. So that's how you find the solution using variable separable. Now let's try to see on GeoGebra on how you can do this. So let me go to GeoGebra. So now here, well, you don't need to install the app for this. You can install, well, apps are available. Otherwise, if you simply go to the Google and type GeoGebra, the site will open. Just click on the start calculator, and then if you see, you can sign in if you wish. You just click on this square and we'll go to cash calculator, computer algebra system. And once you go to this cash calculator, GeoGebra has a function which is called as solve ODE. So once you click on solve ODE and you enter, see if you see the second one, solve ODE f dash. Now what you will do is you plug in a value of f dash over here. Now what is my f dash? if you see from here, our f dash is nothing but 1.4 minus 4y. So if I put 1.4 minus 4y over here, 1.4 minus 4y and enter, this is what the solution I get. And if I make this slider run, the point is also this, they have just taken one point for reference. So all these curves are the solution curve to the given differential equation. So as my C is positive, I am getting the curve over here in the first and the second quadrant, and as my C will become negative, you will see that it got reflected third and the first quadrant, and then fourth in the first quadrant. And as you can see, this solution matches with our solution. So what was our solution? 1.4 upon 4, which is nothing but 7 by 20, minus C upon 4 e raised to minus 4x. And if you want, you can call minus C upon 4 as another constant C, and that's what, if you see, you get here in GeoGebra. 7 by 20, which was 1.4 upon 4, and minus C upon 4 you call C1, another constant, and this is the solution. Now the next thing is something called as the initial conditions. Now what are initial conditions? So there is something called as initial value problem. So what is initial value problem? Initial value problem is nothing but it's when a differential equation is given to you and some initial conditions are given to you. Then this together is called as an initial value problem. So here I have this general solution over here. Now suppose some condition is given to me. So what I want to find a particular solution. That means what? I want to find that solution such that when I put x equal to 0, my value of y is 10. So when such an initial conditions are given to you, we use this initial condition, we plug in the general solution, and we find the value of c. That's what I have done over here. I have found the value of c, which is minus 38.6, and then you plug in over here. So this gives me a particular solution. As you can see, there is no arbitrary constant involved over here. So the last one is nothing but the particular solution. And if you want to see this on GeoGebra, then what you do is either you can explicitly mention that curve, which is nothing but 1.4 plus 38.6 into e raised to minus 4x upon 4. Either you explicitly mention this, or you go to the GeoGebra and you simply type over here. Okay, let me remove this. You simply type over here solve ODE. If you see the third one, points on f. So if you just type your f dash, which was nothing but, what was my f dash over here? My f dash was 1.4 minus 4y, and what is the point? My point is 0 comma 10, means y of 0 was 10, and if I do the enter, it will give me this specific curve. And if you see this 0 comma 10, your curve is passing through 0 comma 10. So you can see here your curve is passing through 0 comma 10. GeoGebra gives you this facility that you put the initial condition as well, and you get this particular curve. And if you don't want the particular curve, if you want the general solution, then you also have the general solution as well. So that's how GeoGebra helps you to find the solution, as well as it helps us to plot the curves. So I mean, this helps you to visualize the curve. So that's the good thing about GeoGebra. It has some flaw also, which I will tell you in the next example. So let's go to the next example. So in the next example, here square root of 1 plus 4x square dy minus xy cube dx equal to 0. Again you try to see whether you can separate or not. If you can separate, then well and good. You can apply this method. So here I have just separated the variables. You just integrate both sides. Left hand side is easy to integrate. For right hand side, you put 1 plus 4x as t. And if you do this simple calculation, which is, you can just pause the video and you can see the calculation. And I get y square equal to 2 upon some k minus, I am calling this minus 4c as k. Okay, I am calling it as another constant. So I am calling minus 4c as k. I have k minus square root of this. Let's see what does GeoGebra gives us. So what is my dy by dx from here? It is xy cube upon square root. So again we do the same thing. I will just type solve ODE. What was the thing? If you recall, it was nothing but xy cube divided by square root of 1 plus 4x square. So this was the ordinary differential equation we had. If I enter over here, then let's see what solution do we get. So it's the same thing. So see what they have done is they have written y equal to, what we had was y square equal to. So if I want to take y, it is plus minus the square root of square root of a minus this, and that's what they have done here also. So if you see this, if I call this below part as alpha, so I can always write alpha as square root of alpha into square root of alpha, and one square root of alpha will get cancelled from the numerator. They have just written in a different way, but it's the same thing. The only drawback you can see over here is GeoGebra takes the solution as a function. So I'm getting y equal to this thing. I should have got plus minus, right? Because if I don't write plus minus, I will get only one side of the curve, which is not the case. So if I run over here, so this is the, if I run the sliders, so I'm getting only the positive side of positive curves, y is positive, but y can be plus minus, right? So that negative part is missing. And why that is missing? Because GeoGebra takes only positive values. I mean, since it treats the solution as a function, and a function cannot take two values, right? So function only takes, it has a unique output. So therefore that's the drawback over here, but that's also fine. If you're not able to get the whole curve, you're only getting the only positive side of the curve, no problem. What you can do is you can go to the graphing calculator. If you see here a square is there, if you click on the graphing calculator and you simply type your equation over here. So what was your equation? Your equation was y square equal to 2 divided by c minus square root of 1 plus 4x square. And if I click on enter, so as you can see, you get the curves on both the side, in the upper half of the plane as well as the lower half of the plane. Whereas when we were in the cash calculator, we were getting only in the upper half because it was treating solution as a function, so it cannot give us two output. But since we wanted the actual curve, we just plotted that equation here itself, and then we can see that I'm getting the curves in both the planes. So that's how it has some drawback, but it's good to visualize and it's free. There are some good softwares, say Mathematica, it's a product by Wolfram Alpha. Also the software like MATLAB, the product of MathWorks, but they are paid apps and the paid softwares, and I am not sure with the copyright issues and all those things. But this is free to use, so that's why I can share with you. So this is about GeoGebra, that how it helps us to find the solution of a first order linear differential equation, and it also helps us to plot the solution curves along with the initial conditions. So that was one thing. So if this both the things are clear, my suggestion is you just try to solve these three examples. Solve using GeoGebra, solve using your pen and paper. I will suggest you both. And yeah, if you have any doubt, you can ask me in the comment section. For the second one, I would like to give you the hint. Here you cannot do the variable separable, but what you do is to replace your x plus y equal to u. You do the substitution, and then you will see that you can easily do the variable separable. Okay, so that is the hint for the second question. So I hope the video is clear to you. If you have any doubt, you can definitely ask me in the comment section. I will be more happy to answer over there. So thank you and have a nice day.